Okay, before starting to even talk about parallel processing, we need to understand what is actually parallel processing and what do we mean when we say parallel processing. So let me put these in order. Perfect. Okay. So to try to understand what parallel processing is, I have to give you an example. And since I didn't have time to eat lunch today, I'm going to make it all about food. So, so parallel processing is like having a burger in a restaurant with fries and Coke. When you're sitting, just imagine that you're passing window of a place that they sell burgers. I don't know, whatever, McDonald's, whatever you call it. And you see somebody sitting facing towards the window, and he has a burger, he has fries, and he has drink. So you pass by, you will see that he's eating, right? And you go back and you come to the other side and look at him again, you see the drink is less, the fries is less, the burger is less. And you go and you pass by again, everything goes down. And it finishes. So from your point of view, the person was eating his meal and the meal was finished. And he was meeting the way you saw it, because when you were passing through, you saw burger got half, fries got half, drink got half. In your point of view, he's eating everything at the same time. This is called multitasking. This is not parallel processing. Multitasking is the one that you switch between tasks so quickly, so a bystander, that standing person over there looking at you who has much slower speed than you thinks that you're doing things all at the same time. That's multitasking. It is not parallel processing. So you can do it with one CPU, that is your mouth. So you have one CPU, that is your mouth. If you just stand over there and watch the guy is having a bite to a burger, puts it down, a fries, a sip of drink. So three things are not happening. They are not putting the fries and a drink at the same time. Everything is happening. I know, you've seen somebody doing it, right? Yeah, my friend does it. No. Well, but yeah, so that's what happens. So that's kind of a thing that happened before, a long time ago, when we had one CPU in a computer. And that's how operating systems actually did multitasking. And then hyper-threading came through that actually split the CPU into cores. And that was the operating system level of multitasking, which essentially, multiprocessing, which would essentially run the programs in several processes. And I'll explain right now what multi-threading is. Multi-threading is watching TV while eating. That's multi-threading. You have two CPUs. One is your eye, the other one is your mouth. You are eating while watching, and it's happening at the same time. We call this one multi-threading. Now, if you wanted to watch, not eat, and then eat, not watch, you would be much slower. Well, because you do them both at the same time, essentially it happens. And unfortunately, our brains are not multiprocessed. Our brains don't work that way. So that's why when you're typing, you're not listening to me. You think you are, but your brain is actually pausing. If you have that capability, it's a problem. No, those people have it. Like, many people are like that. And they have some kind of a problem. Many features of autism is like that. But in other processes, they can't do it. I'm one of those. Anyways, so I cannot multiprocess. I have other issues. But anyways, so that's what it is. Now, we want to learn how we can actually do parallel processing and how it works. For that, we need to first, so let's understand that multi-threading is a software level concept. Hyper-threading is a hardware level concept. So if you're saying that the program is hyper-threading, that means the process that is being executed is being split between CPUs at hardware level. You have no control over it. Hardware is dividing the work and trying to do things faster. But parallel processing is done in software level. Now, threads. Before C++11, C++ wasn't a multi-threading language. It was a single-thread language, which essentially any program that you have written down to this point. You write a program, something happens, and while that thing happens, nothing else happens. And it ends and goes to the next one, and next one, next one. Everything happens in a sequence. And to be able to do multi-threading, you had to actually bring outside libraries, install modules, outside modules that were written for C++, not by the compiler, but by third parties. You paid and you bought those things to be able to parallel processing. But when C++11 came out, it actually, threads were introduced in C++11. After C++11, every single C++ program that you're running is a multi-threaded application. But you're only writing it in one thread, that is main. So let's understand that. So the main that you are running is actually a thread running. A thread is a process that is happening independently from other processes. So with a multi-thread program, we're going to teach you how to write 3 mains. And all 3 run at the same time. That's an absolute right. It's not 3 mains. You are actually writing the main, but inside the main, you can call a function 3 times at the same time, execute it at the same time. So if you create, say, 2 threads in your application, how many threads are running? 3. 1 is the main, and 2 are the ones that you created. Okay? So remember that. That's something that we need to understand. The program that is running by itself is a thread. So let's talk about threads. And we have to understand something about threads that is extremely important. We have to understand the mechanism with which they work. And for that, I'll do this. I remember I had to turn off something for it to be. Yeah, there you go. That's good enough. So when we are doing threads, you always start with 1. That's main, right? So you start with, your program starts with 1, and over here you create a thread. So essentially your main continues to running, and a thread runs parallel with it, comes down. Now you can have more threads created, it doesn't matter. So they all run in parallel, literally, okay? But if you just leave it like that, and let it continue and program ends, you'll be in trouble. Because as the program started as 1, it should end at 1. Which means when you create several threads, you have to make sure that the threads are what we call joined at the end, back to 1. If you forget to join a thread, your application will be inconclusive. One of the processes will, it's like memory leak, but with process. It means you have a process hanging and it's not ending. So their outcomes and results are not identified. You can't say what. You have to join them back into 1, and then that 1 terminates at the end, and that's when your program is done. So remember, creating a thread, it should always end with joining that thread. So when you create 1 thread, you join that one back into this one. And at the end, you're going to have only main. Are we okay with this down to this point? Okay. So to use threads, we include threads. Okay, so, and the syntax for it is like binding. When you bind a function to arguments, remember what we did it? Like when we wanted to, we had a 3-argument function, we want to call it as 2, and we actually bind it with 1 argument. So the bind has the same syntax of it. It's a wrapper. So essentially, a thread is a wrapper around a function and calls it in parallel with the thread that it's splitting from. So essentially, I can have, for example, a function over here. Let's call it say hello. Okay. So the say hello is going to run like I want the say hello to run in parallel, and then in here I will say thread. And for the thread, let's call it T or whatever, okay? And to that thread, I'll send say hello. So essentially, it works with a pointer to function, functor, lambda, any type of executable you tell to thread, that's say hello. So, and it's RAII, so resource acquisition is initiation. Resource acquisition is initiation. I hope that I'm saying it right. Google it right now, write it on and see what it is. RAII. It means as soon as you request for the resource, it starts. It's not that you can, what does it say? Initialization, it says. Okay, so initialization. So resource acquisition is initialization. So as soon as you ask for the thread, it runs, which means immediately at this moment, it will run. But if I just leave it like that, I'm in trouble. At the end, I have to join it back in. Now I have to say t.join. Now I have a thread. So like this, I'm going to have 2 processes running with that cout and this cout. Okay? So you see it says, and take a look at this. The way I wrote it, say hello should run before that, correct? But when a thread execution is happening, there is no way for you to tell which one is running first. It's, I couldn't say random, but yeah, you cannot say. It's unpredictable. They are all running at the same time. So there is no, remember, when you are running threads, time is parallel now. You have 3 things running at the same time, 2 things running. You cannot say which one is running first. Yes? Mm-hmm. Oh, yeah. Oh, we have lots of mechanism to do that. We have many things to go through. Don't worry about it. So we can control that. So first, let's learn how they work. Then we're going to see how they can communicate. Like if you have a variable over here that 2 threads are using, how they're sharing it. If you want to extract information out of a thread, how you're going to put them all back in something. If it's a shared resource, how they're going to compete on resources. So all those things we're going to find out, and then through that we're going to come to locks and mutexes and things like that. And you see you can lock a thread, and we'll go through that. Okay. So to have a better demonstration, so in here I'm going to say A. Where'd it go? Oops, wrong button. Okay, so what the heck? Grammarly? Really? This app is obsolete. I haven't used it for a long time. I thought I didn't even uninstall it yet. It doesn't have an app anymore. Anyway, so let's have another type of thread. So take a look at this. So I have foo. Foo receives some kind of a signature and prints it 100 times. We okay with that? And then I have a function called threads that is creating two instances of thread X and thread Y. And to one of them I send the caret, and the other one I send the dash. And then in thread, I'm going to call a third one that is a foo, and I'm going to pass underline over there. So 3 foos are happening at the same time when calling threads. We okay with this? All right. So now I'm going to say over here threads, and let's see what happens. Take a look. You see that pattern? Remember it. Now take a look. Now take a look. Now take a look. Every single time it has a mind of its own. Definitely 300 characters are getting printed. But what is the order? You really don't know. It all depends on the number of processes that are running, the CPUs, and especially right now I'm not running a standalone application. Usually when you are writing a multi-threaded application, the computer you are writing is dedicated to run your application, like you're writing a web server or you're writing something to process. And the computer that is running the process is not supposed to watch Netflix on it. You have it for a purpose, right? If that's the case, then you can actually see how many CPUs do you have on your computer and exactly create that many threads so you have the optimal number of things running. And when it's running, music is not going to get played. And I'm not going to be sending lecture online like that, because right now I'm using Blue Button. So all these things are happening. Although I have several CPUs on this computer, but they are used for many different tasks. It's not this, right? So again, it's trying, but hey. Okay? Are we good down to this point? So we understand that multi-threading has no, they have no way of predicting what happens when. And the next example that I have over here is going to run a function that requires reference of something. See that? So What happens over here is that in this for loop of mine, I'm doing something with these characters and I'm printing them out. But I need that reference of num to see exactly how many things are getting printed out of those characters. So essentially, I have 10 characters over here, and 10 times I'll go from 0, or I have 50 characters over there. 10 times I'm going from 0 to 50 and printing those things out. Just doing something. But I have a reference of a number that is coming in, and I want to set that one so I can see what is the value. Why am I not returning it? Threads are not capable of returning values. With threads, you can only receive references and modify references. With threads, values cannot be returned. Why? Because you don't know when it's going to get returned. For that, we're going to come to a mechanism that is created in future. I use this word. In future, I mean later that I'm teaching. And the concept is called a promise and a future. So you can actually make a promise in a thread and in future get the result. So we're going to have a promise object and a future object. We're going to come to that. And that's returnable because you are asking for a promise, and in future you receive the value back when the thread is joined back in. Okay? You cannot receive anything back from the thread because it's not joined yet. You can't do that. And when it's joined, when you want to join it, you don't have the thread. So you can't return anything, right? So because of that, we have to pass references to a thread. But remember when we're binding a function to a specific type of argument, to pass the argument, we couldn't pass a reference. We actually had to do a ref in front of it. We had to say reference of something. Otherwise, it would always go by value. Remember that? So we need to do the same thing over here. So essentially, say I have 3 variables. Say I have 3 variables over here. And these 3 variables, they all have zeros. And now what I want to do, I want to call that foo thingy and pass a reference for x for the first one, y for the second one, for the second thread, and m for the third thread. And I want to pass a series of characters for it to print. Okay? If I want to do that, so what I need to do is to do something like this. So essentially, say thread tx is equal to thread foo is the function that is being called, exactly the syntax of bind. So foo is the function that is being passed to this thread. Reference of tx is the reference of this that is being passed to it. If you don't put ref, it's going to be by value. You're not going to get anything back. Remember that. You have to wrap it around the reference wrapper. Okay? And then I'm passing series of carets to it. So that's my first thread, and as soon as it runs, it's going to start running it. And for the second one, I'm going to pass the reference of ty, and this time I'm going to pass a few dashes to it. Last but not least, I'm just going to call the function like a human being, because that's a thread, right? So now I have 3 threads running at the same time with 3 different things. So dashes, underlines, and carets. And it's going to go through them and run them one by one. Obviously, what I need to do is to join tx, join ty, and now at the end, I can actually see who returned what. And that's how you get values back with a reference. So tx is going to get this many characters, ty that many, and tn this many. Okay? Obviously, because they're all running at the same time, you're going to have mishmash of stuff being printed. But you're going to know, oh, But you will know that TX printed 60 characters, TY 120, and the main thread printed 240 characters. Are we okay with this? No, they're not random. They're functions running. So function will always run at the same time. We'll come to the randomness of characters later on. We're going to come to the randomness later on, but let's just grasp how the syntax works. So if you look at the syntax, this is how it works. So if you want to pass reference of something to a thread, you put it in a reference wrapper, and then you pass it through, and then you can pass arguments. So I'm saying call foo with reference of tx and that address. Call foo with reference of ty and that address. We okay with this? Are we okay? All right. Baby steps. I'm not rushing. I'm very slowly we are going forward. Args and references. So what if I want to have a common resource between the things that I'm printing? So what I'm going to do now is writing the function like this. Okay? So I'm going to say I have a print function that it gets number of seconds, and from now up to number of seconds prints characters. I want to see how many characters are printed in 2 seconds, for example. All right? You okay with that? So it receives number of seconds. Now, what I can do is to create my threads. So now we know how the threads are called. I'm not going to bring them one by one. I'm just going to show it to you. If you see, if you think I'm going too fast, let me know, okay? So this is going to complain. I don't need to initialize this, but because I'm setting them in the function, but I'm going to set it anyway to shut it up because it tells me you're doing it. So I'm creating 3 threads of PRN over here, okay? And I'm going to say seconds now plus whatever seconds I have, 1 second. I want to know how many characters in 1 second is going to get printed. Then I'm going to say run the thread for print, pass this number, pass the second, pass the reference of tx. So what happens is that as you see, I'm not sharing. I am sharing things by value. There's no problem over here. I am telling them to read from seconds. Remember, if I don't reference wrap it, it's going to be by value. So there is no problem. And I'm not, even if it was referenced, I'm not changing the value. I'm just reading it. And who cares? You know, it's like 50 people standing looking at the sign. They all read. There is no problem. Okay? But 50 people want to write on the same whiteboard at the same time, then we're going to have a race condition. Okay? So now if I run this program, you will see that we can now actually see, essentially they are competing with each other to see how many things they can print. And the first one, you were saying, are they always the same? Now they're not, because they are really competing. 5,000 over there, 4,000, 5,400, 4,300, and 5,600. Okay? One more time I run it. You see? The first one is now 5, the second one is 6, the third one is 58. So now they're really competing. The funny thing is that if I actually print the total is not going to be identical. It's going to be different. Because remember that this is racing against lots of processes happening in the computer. It's not only that. So it's possible that in 1 second, if it was only 1, it could print 5,000. The next time the CPU was in a more unoccupied mode, and you could print 8,000. So I don't know. So if I put all the things, still I cannot guarantee that it's going to be the same. Are we good? You want me to print the total too? Just does it? So we suggest. Oh. Okay, so that's that. So this is going to be when you look at the, if you read the threads, you see I can teach it in 10 minutes. Go through it like that. But this is something that you really need in future if you want to write efficient programs. Okay? So anything that you see I talk about over here, and it's not in the notes, it's not going to be on the test. So there may be stuff over here that is not over there. So be aware of it. For example, thread classes, I don't think it's covered that much, because thread is pretty tricky. We'll see we have easier stuff. And especially when we go, all the things that you're doing right now, you can, like, instead of writing 3 threads, I can actually write an STL library, call it STL, and say run this one 3 times and in parallel, literally. And it does everything by itself. I don't need to worry about creating threads, anything like that. So all those things are already there. There is an STL library for it. Now the problem is when we actually want to write on the same thing. So now I have a counter, and I'm passing the reference of the counter on to the 3. And every single time they're printing something, they're counting. So now it's not 1 second. I'm just counting the numbers, right? Now, all 3 of these guys want to count at the same time and to write it at the same time. Can they? Oh, it's not. It can't, because they're going to be race conditions. They're going to be moments that they are both writing at the same time, and they both think that they added 1. That they really added 1. The value was 2. 2 processes at the same time added 1 to it. What happens? Exactly at the same time. It becomes 3. It doesn't become 4, because the one is not waiting for the other, right? There is it's not like a washroom that you go to the doctor's office and you get a key. And when you go there, the second person cannot go because they don't have a key. We're going to teach you how to do that. That key is called a mutex. We could actually give these function, I could give that function a mutex and say, when you get in, lock the door. Or when you are writing on a counter, when you're increasing the counter, lock the counter. Write it, then unlock it. Then when it's trying to lock, when it wants to write beforehand, it wants to lock it. It waits for the key to become available. As soon as it becomes available, it locks it, it becomes unavailable to everyone else. It adds 1 to it, then unlocks it. As soon as it unlocks it, everyone else will race to get the key. The first one that gets the key locks it, then everybody, we're going to teach you how to do that, but now it's not happening. So the results are, oh, that's both 1 or 2. That's interesting. It's all luck. Okay, so you'll see. Run it and you'll see what happens. So I am doing the counter and I'm adding the 3 to see if they are the same or not. But you will see later on that you run it a few times and you'll see this, sometimes it's going to come out different. So writing common, there's no guarantee that what you are writing onto will actually take effect the way it's supposed to. which brings us to the concept of race condition. So a race condition happens when multiple threads across the application that you are writing try to write on the same process. And what happens, they try to actually compete with each other which one's going to write. And every now and then it happens that two of them want to write at the same time, and the process doesn't come out right. So it literally, literally creates an unpredictable behavior. A simple example for it will be something like this. I wrote a complicated version of it, so what do I write? I'm going to call it, let me see, the E, writing on common, on shared. Oh. So this is an example of a shared condition. So this is not thread safe, they call it. Okay? I did the exact same thing over there. So this plus plus that is happening over here, it's very possible that it's not going to be 200,000 after I'm done. So let's try it and see if we are lucky and we're going to get the counter wrong, hopefully, and we'll see what happens. Fingers crossed. There we go. Hey, finally. So as you see, it's supposed to be 200,000, but it's not, because there was a race condition happening on the counter. Okay, the other one I was just doing 200, it didn't work properly, but this one shows it. So this is something that we have to be extremely careful about. Calculations may not be right if you don't actually do the proper locking mechanism on the shared memory that you have. Oh yeah, exactly. So this is race condition. You have which brings us to what we call atomics. Now, the race condition that I have created over there, let's see if it's going to work. Oh, what did I do? Okay. Let me see if anything, because suddenly everything got. People at home, can you hear me?
Yep.
Okay.
Yep, we can still hear you.
Okay, perfect. Thank you. So what atomics do, it creates a thread-safe variable type that ensures that the processes that are happening is happening in an atomic way, which essentially means there's no race condition. So when I create atomic int counter, counter becomes an integer that is atomic. Okay, you will see now. I'm going to run this, and you'll let me just show you. It says always 200,000. And that's what happens. Okay? Atomics are not as simple, okay? But I'm just giving you a hint. Atomics have methods that you can actually use to see. So you will see that just adding to an atomic is not a safe way of working with it. Okay, forget about it. So just for now, it's not in the notes, atomics, but something that for you to know. I'll go through it more in detail later on. Okay? Pardon me? Yeah, so what it does, essentially, it locks it before it does anything to it. So the plus plus operator is overloaded before you want to do something, it locks that value. So the second process wants to do it, it will not be able to write on it until it's released. So it puts the mechanism inside. But you will see later on that there are things that you can do. You can you add a value to an atomic, receiving its old value. I don't know if I'm making sense or not. So there are methods that you can, because when you add something, if I add one to this atomic and I want to check the value of counter and do something afterwards, can I? No, because the process is added, and as soon as the 50 other ones are going to work with it. So there are methods that you can say add one, and then you can receive the old value. Tell me, what was the value before I added one? So you can see if the value you had is what you want to make the decision for. You follow what I'm saying? I cannot, am I making sense? So what I'm saying is that if I'm supposed to pour a cup of tea for myself, and 3 other people want to do that, okay? If I want to know if I have successfully done it or not, or whatever, so when I actually pour the tea over here, okay, and it gets full, after I pour the tea, I am asking, what was it before I poured the tea in here? Was it empty? How much tea it had in it before I poured into it? So I can actually see what I had before matches what I need to have after. A very complicated thing. Atomics are very iffy when you work with them in different stages. So in one stage, as a counter like this is perfect. But if you want to do 3 things back to back to counter, then it's going to be all over the place. So one action on it, fine. But if you have 4 different ones, you don't know. Maybe right after this, another process reduced it by 1. You don't know. You know what I mean? At that moment, it's atomic. But if you do it again, then as soon as it comes out of this process, line 9, some other thing may change it. Careful. Don't think that if you have an atomic value in here, it remains atomic throughout the whole scope. That is not the case. Only the operation is atomic. There is no race condition. But after, if you have another one, so if the first counter over here is added by 1, if you go to the next one, then it may be 2. So I cannot check the counter in my for loop. Am I making sense? Okay. Having said that, having talked about atomics, so again, remember this atomic is a wrap. Now you appreciate when we use the word wrapper. Okay, everything in STL and C++ library, they are all wrappers around variables to control the action that you are doing on it properly. Okay, so atomic is a wrapper around something to make sure that the operation happening to it is an atomic operation. So now, did I show the lambda thingies for the threads, or I did not? I didn't. So, sorry, I should have done it. I didn't do it. But anyways, potatoes. Lambda function doesn't make any difference. It's just easier like this. I just passed the lambda. So, in here, if you recall, we had that clock thingy running, right? In a function, I just have it in a lambda. So I'm going to say tx is what? 0 starts, and I'm receiving everything by reference in the code. So tx is 0, clock now minus seconds, and I want to see how many things are printed in 1 second. Okay, and the values are passed back into tx and ty. Are we okay with this? And again, not to have the compiler complain, because it doesn't know I'm setting it in there. I'm going to do it like this. Okay? Now in here, I'm saying cout go, and I'm going to say join, right? It's like it's a race I want to say go. Can I? My question is this. So if I actually do this, where did go happen? At the top? Yeah, it did. Lucky. But not necessarily. It could happen after. You've seen it. I've done it the other one, and it happened after. Remember that? So there is no guarantee for this. I want to give the example. Sometimes it works, sometimes it doesn't. So there is no guarantee. You cannot say go to a thread and it goes, because everything is happening at the same time. As soon as you create the thread, it runs. So you cannot say if this go is actually holding it. So for that, so this is an unpredictable ready go. I can use an awful way to create a ready go that actually I can control. How is that? Using those variables that I have, I can create a pause in my function. Take a look at this. So in here, I'm going to say who goes, okay? And that's no one, right? So n means no one's going, right? Then in here, I'm going to say while who goes is not equal to x, keep looping. It's not that I'm actually stopping the thread. I'm just putting it in an endless loop. Okay, so now these two threads are running full speed, but around themselves, until I set who goes to x. And then the thread for this one gets released, and the rest will get executed. So threads are a little crazy. So think about it for a second. The while loop is running. I'm going to change the value of who goes somewhere else. And because it's running in another process, it's going to release the process and it will go. Am I making sense? Remember, these processes are running at the same time. So essentially what happens, main starts, thread tx starts running, while loop goes endless because who goes is n. Okay? So it keeps going endless over here, and it's running. And this one runs perfectly. Okay? So they are both running. But they are running at the first line because it's an endless loop. Then I'm going to say who goes is x. As soon as I do that, the condition over here becomes false, and poof, continues. And this loop ends and runs that one. Now I can decide which one I want to run first and next. So, and then I can join it afterwards. There's no problem. So when I actually run this, you will see that it actually sequences the things. It's not mixed anymore. Kind of defies the purpose, but I just want to show you how we can control this. We could just have two function calls. I know, but I'm just saying that. Give me a second, and you'll see what is the reason for this. Do we understand? Are we okay with this? Oh yeah, but it's a very awful traffic light. Your CPU is not at rest at that moment. It's working full force. So that thread of yours is consuming CPU power and usage by giving something dumb to it to do. Just turn it on yourself. That's it. That's what it's doing something, right? So that's not a good way of doing it. So yucky, ready, go. If I can type it. Okay? And this brings us to mutexes. Remember we had that programming here, race condition, right? If I could somehow stop the race condition and lock the door and don't let them kind of manually make this thing atomic, then it wouldn't go wrong, right? If somebody was changing the counter, I said, everyone else stop, and I could work with this. That is done using mutexes. So take a look at this code, and I'm going to tell you exactly what mutexes are. So you have to first include mutex. So you create a mutex. Mutex is essentially you are creating a door, a flag, something that processes can actually lock and unlock. Then what you do, you say, oh, I'm using lock guard in here. Shoot, I shouldn't have. Damn it. No, sorry. I'm going to show you the manual one first. I'm using a lock guard over here. My apologies. Let me bring the other one up. This is manual, okay? So I have the mutex, so it is exactly the same thing that I did with the other one, but now the difference is that I create a mutex and I call it key, okay? When I get into the thread, I'm going to say lock. What does it mean? It means anybody using that key, if they want to lock, if the key is already locked, they have to wait. And see, lock, lock. You see, the threads that are running right now, in each function in those, now it could be one function at the top, it doesn't make any difference. Now they're just two same lambdas that I'm running, it doesn't matter. But the point is that they are locking the same mutex. So the first thread at line 12, when it runs, it says lock. It looks at the key. If the key is unlocked, it locks it. As soon as it locks, it means the process, because it locked it, it can continue with its work. It goes through everything and runs everything and unlocks. Let's assume while it's doing this, the second thread is running. It comes to the key and say it wants to lock it. It says it's already locked, so it has to wait. Now, if I have 50 of these processes happening at the same time, they would all wait for the key to get unlocked. As soon as the key is unlocked, they're going to race and see who's going to get it first. The first one gets the key and locks it, locks everybody else out, continues its process. So like this, then these two processes cannot run at the same time. And now I locked it right over here. You see that? Now I'm going to say go. First, because it's locked, nobody's running. In main, I say lock it. So nobody's running now. All the threads are waiting. Now I'm going to say go. I'm going to say key unlock. Now I'm unlocking it. And poof, they go. Okay? Easy as that. Then one by one, they're going to unlock and go and join. And you will see that like this. Then you will have, again, you cannot for sure say which one is first. Now this one is caret is first, underline was first. The other, again, underline. It's 50% chance, I don't know. I'm just flipping a coin and unluckily it's good. So it could be the other way. Just take my word for it. Okay, we don't know which one is coming first. But because it's unlocked, it's impossible for it to go. Now, the problem is that if you forget to unlock a mutex, you're screwed. The whole program hangs. Not the whole program. Any thread that is using that lock hangs. Huh? Uh-huh. It's possible that it's going to just hang because you want to join it back over here, right? So it's going to wait for it to join. So this is going to lock it. It's going to execute everything, comes back and joins, right? The other one wants to join. It wants to run. It cannot lock it. What happens? It have to wait for it. So it's never going to join. Probably it's going to just hang. I don't know. Let's remove it and see what happens. Yeah. And this time it was caret that happened first. Right? So it's just going to stop. It's not going to go. Okay, so if this was a standalone application that you have written, it wasn't in the virtual environment of the IDE, that would always hang. You could not stop it. It would just run in the background until you reboot your computer. So one of your processes would have gone nuts. But, okay, so how can we guarantee this? How did we guarantee that a pointer would not have memory leak? What did we do? No, but how? You have a quiz on it. How did smart pointers? With smart pointers, we wrapped a pointer inside a smart pointer and created a destructor for it, right? They did the exact same thing for mutexes. That's called a lock guard. That's why I said I'm not going to show that first. Okay? So the one that I showed you 2 seconds ago, and I said I'm not supposed to show it to you. Oops, they all start with thread. How do I know which one was it? Was it this one? Yeah. So you see over here it says lock guard. So essentially lock guard says there's a mutex and lock it. So it says create a lock guard for a mutex. Okay? Lock MTX. What happens? It creates an instance of a lock guard over here and locks a mutex. When the scope is over, that lock dies, right? In its destructor, it unlocks the mutex. Ta-da! So, so by creating something like that, then you're guaranteeing that it's not going to be a mistake. Even if you have a thread and you're jumping through a thread and stuff like that, it's going to actually destroy it. Okay, it's when it goes out of scope, it's going to get destroyed. And that lock guard guarantees that you are not going to have any problem with it. So when you run this, then you will see that this is going to be always 200,000. Okay? Okay? So the exact same thing for those, the function that we have written with the lambdas. That's the lock guard. Okay? So I'm doing the exact same. Instead of creating a mutex, I'm creating a lock guard. So I don't have to unlock it anymore. It's the exact same thing I have done with that ready go thingy, but it's with lock guard. So it's impossible for me to hang the program. I'm not going to run it. We know what the outcome is. Which brings us to after C++17, a new lock guard was introduced that they called it scope lock. Okay? For our level of understanding, it works exactly like a lock guard. Okay? But the difference is that with this, you can have several mutexes. So in this lock guard, you can have comma, you can have 3 mutexes over here. So you can lock 3 mutexes. And that prevents a deadlock that happens with a lock guard. With a lock guard, you can have deadlocks, which is essentially two functions. One locks the other. There are 2 mutexes, locks the first one, and then locks the second one. The other one locks the second one, then locks the first one. Because of that, they are both waiting to lock a. So I'll show you. So this is scope. This is KJ, JKL. Ready, go with scope lock. So essentially, this is the, where did I put it? So although lock guards are safe, but they might cause this problem. Okay? So this is what happens. Task 1 locks MTX1, waits for MTX2. Second one, MTX2 waits for MTX1. Therefore, they're always waiting for each other to unlock the thing. And it's a lock guard. You see that? So the first one locks. The second one comes over here, locks 2, and it wants to lock MTX1, it hangs. They're waiting for each other to unlock because they were using 2 mutexes. So that's called a deadlock. Now there's a solution for it with C++17, which is the scope lock that I just showed you. So I said scope lock is exactly like it's exactly like a lock guard. No, this is what it is. This is the solution for it. So if you have 2, you simply say scope lock MTX1, MTX2. It makes sure there is no deadlock. So you can lock 2 things and relax. They're not gonna deadlock each other. You don't have to follow certain sequence, because if you have 2, you have to make sure you have to go to all the other functions and see if the sequence of the locking matches this one. But in here, it takes care of it. It makes sure that they are locked in proper order and so on and so forth. So deadlock will not happen with this. Okay? So if you have multiple ones, make sure you have C++17. And in your C++17, you use scope lock instead of. There are more locks, but this is too rich for our blood already. Scoped lock to prevent deadlock. Okay. Okay, it's 2:44. I already ate your brain enough. I know anything else that I'm going to tell you is not going to fit. So starting with vectors and stuff, I'm going to tell you after the quiz for the smart pointers. Okay, so we're going to go right up to have it considered because I have to go to vectors, then I have to go futures and promises and stuff like that. It's too much. So digest this. These ones, go at home and run them and try different ways of doing it, and you'll see how they work. Another thing that you might find useful when you're creating threads, if you want to see actually how many threads you can create, I can give you this one now. It is hardware concurrency. So to see how many threads is best, okay, I have to show. So let me show you this first. This is number of concurrencies that you get. So if you actually do this, it tells you how many threads is your computer capable of running. It's 8. So this one has 8 CPUs. Okay? So it tells you, like, if you make 16, then it's got to be multitasking. You have to go 8. 8 is the best. 8 is the number of CPUs that you have, and it's real multi-threading happening. You have 8 processors that are running. If you put, so what happens is that up to a certain point, even multitasking makes things faster. But as it has a certain thing, when you go a little higher than a certain amount, now you can go to CUDA programming. I think I don't know what was the subject name. That you can put a graphic card on your computer, and a graphic card has 4,000 CPUs in it. You know, graphic cards like that, right? They have CPUs that are specifically made for certain calculations, not as complicated as an i7, but they're CPUs. They have 4,000 of them. And those, you can run things like, because now you can run your application on 4,000 parallel things at the same time. Okay, this has 8 CPUs because it's 8 i7s. So, but those ones are specifically made for certain calculations, you'll see. So, exactly. That's why all the computers that have like, who is the company that is providing AI processing now? NVIDIA. And NVIDIA is the graphics card, right? So that's what they do. That's what they create. So they focus on specific calculations that you need to do, and they create CPUs small enough just to do that, and they make thousands of them. And then you can do things fast. Yes? Always depends on your hardware. Of course, if you go 20 years back, more than that, like we used to get, like, you guys are not that old, but I remember I had a computer to be able to do things. I had to, what we called the coprocessor. We had to install that to do floating point calculations for us. Otherwise, it would be very slow. That's my era. But that's the time that we had one CPU, and beside it, we put something that it had to do floating point operations, and it made it faster. I'm like, wow, my game is running much faster now. It's like, and I had to running like old TV games. But anyways, but now these days, yeah, my cell phone has 8 cores right now. My cell phone has 8 cores. 8 separate cores, not like, you know what I mean? It has 8 CPUs in it. So, yeah. So keep that in mind. That remember that you can have a vector of threads. We'll continue with this the next time you're coming in. And I'm going to show you how to put the threads in a vector and then join them all at the end. Like that, it's much faster. And you can create the number of threads to the exact number of processes that you have. Yeah. Questions? Huh? No, you cannot. You can, yeah, maybe if you make it so up to 8, it becomes faster. When you go 16, it becomes faster, but not as much. When you go to 32, then it becomes slower because the overhead of passing the tasks around supersedes the process that you are doing, makes it slower. Yeah, exactly. Yeah, it's exactly. So again, it depends on your task. Like if I have 1, 2, 3, 8, 5 rows over here, 5 people cleaning the tables is efficient, is very fast. If I put 20 people over here to clean the tables, it's going to be a mishmash. Oh, you go with me, they cannot pass through. It's going to be longer. So it's better not to do that. You have to, that's why we have that concurrency. Number of processors. So we are doing down to here, and I didn't even give you a break, which is okay. You are going earlier. Next day, I'm going to post this one's going to be, I think, an easy quiz. So, because you just have to use smart pointers, right? So probably the question is going to be something like, I'm going to ask you to, I'm going to give you a class as usual. I'm going to say, write a function that creates a dynamic object and returns a smart unique pointer holding the dynamic object. And in the other one, I'm going to say, receive that smart pointer and create I don't know, 50 scope, what do we call it, shared pointers to, I'll go something crazy like that. And I just want to see if you know the syntax. You'll see the quiz. Last night when I was sleeping, I designed the quiz. I'm like, yes, I'll do that. So I forgot what it was. Yeah, I always have to remember, and it's something that I did as a young programmer. I had a notebook beside me, and beside my bed, and I solved stuff in my dreams. Like I would dream of a solution, and I would wake up and write it down, and the next day I was in heaven. So it happens. When you think about it, it happens. In dreams, you can solve problems easily. Anyways, have yourself a beautiful day. And the people at home, any questions?
Nope. Thank you.
Thank you very much. Have yourself a beautiful day.